Hey there and welcome. Today we're going to talk about identifying and using the 7 basic exponent rules. So let's go ahead and get started because there are a lot of them. Alright, so our first rule is called the power rule. And it says that when you are multiplying the same base, you're going to add the exponents together. So in this example, I have my base of a to the m times my base of a to the n. A is my base, it's the same exact thing, so I'm going to take those exponents and add them together. If we're looking at an example with actual numbers attached to it, I have 6 to the 5 times 6 to the 3, which gives me 6 to the 5 plus 3, which is 6 to the 8. We're just taking those exponents and adding them. All right, my quotient rule. When we're dividing the same base, we're going to subtract the exponents. So I have my example here. An actual worked out example, 6 to the 5 over 6 to the 3 equals 6 to the 5 minus 3, which is 6 squared. Now, the reason why this works is because 6 to the 5 divided by 6 to the 3 really tells me that I have 5 6s up in my numerator. All right, 1, 2, 3, 4, 5. I have 3 6s in my denominator. And I know that when I do a 6 divided by 6, that just gives me 1. So this 6 divided by 6 is 1. This 6 divided by 6 is 1. This 6 divided by 6 is 1. So those 3 sets of 6s are no longer there. We've eliminated them by changing them to 1s. So all I'm left with on the top is this 6 and this 6, so 6 times 6. There's nothing left on the bottom, so it's automatically a 1. It's not a 0. It's a 1, because remember, we're always secretly multiplying by 1. We just never write it. And so I've got 6 times 6, which is 6 squared. Yes, it is also 36, but 6 squared is where we're going for this example. All right, my next rule is called power of a power rule. And so that's saying when we have an exponent being taken to an exponent, we're going to multiply those exponents together. It doesn't matter what the base is, we're focusing on those exponents for this one. So if I had 6 to the 5th cubed, right, 6 to the 5 to the power of 3. That's really saying 6 to the 5 times 3, which is 6 to the 15th. The reason why this rule works is because if I have 6 to the 5 to the 3, that's telling me I have 3 sets of 6 to the 5th power. So I've got 6 to the 5th times 6 to the 5th times 6 to the 5th. And based on our power rule from rule number 1, if I have the same base, I can add those exponents together. So 6 to the 5 plus 5 plus 5. 5 plus 5 plus 5 gives me 6 to the 15. Rule number 4, power of a product rule. So this is saying that if we have multiple bases, so more than one base, an A and a B, a 6 and a 7, a 2 and a 9, we have multiple bases that are being taken to a power, we're going to distribute that exponent to each base. So if I have 6 times 5 cubed, I have 6 cubed times 5 cubed. And the reasoning for this is the very, very same as that previous rule, power of a power rule, right? It's showing up 3 separate times. So I'm going to have 3 6s and I'm going to have 3 5s total. All right, rule number 5, power of a quotient rule. If multiple bases are being divided and taken to a power, we're going to distribute that exponent to each base. So very similar to power of a product, but this time it's just division. Same exact reasoning applies here. So if I have 6 fifths cubed, that's really 6 cubed divided by 5 cubed. All right, rule number 6 is the 0 rule, and it's my personal favorite rule. And it just says any base with an exponent of 0 becomes a 1. There's a 0 as your exponent, that base turns into a 1. That's all you need to know. So if I have a to the 0, that's telling me that in my problem, in my example, in my whatever I'm working on, I don't actually have any a's. There's none. There's 0. That exponent's telling me there are 0 of them. But remember, we are always multiplying by 1. We don't show it, but it's always happening. So we're left with that 1 that's there. The a doesn't exist. That exponent tells me there's 0 of them. So we're left with the 1. Similarly, 6 to the 0 equals 1. This big, huge, gigantic number to the power of 0 equals 1. That exponent is telling me that there are none actually there. But I'm always multiplying by that 1. All right, our final rule, rule number 7, the negative rule. any base with a negative exponent needs to be flipped to the other side of the fraction bar. I don't know why, but this rule seems to be the one that people have the most struggle with remembering. If the exponent is negative, it does not mean that your base is negative. It means that it's on the wrong side of the fraction bar, and we need to take it and flip it over. So if I have 6 to the negative 3, I need to flip it over the fraction bar. So instead of it being in the numerator, that 6 with my base of 6 with my exponent of 3 needs to go down to the denominator. And you notice when we flip it over the fraction bar, our exponent changes from negative to positive. Similarly, if I have 1 over 5 to the negative 2, the 5 to the negative 2 is in the denominator, and that's okay. But it can't stay there because that exponent is negative. We need to flip it to the other side of the fraction bar. So it went from the denominator up to the numerator. So it becomes 5 squared. Remember, when we flip it over the fraction bar, that exponent becomes positive. The same setup works for fractions as well. If I have 4/5 all to the negative 3, I'm going to take that negative 3, I'm going to take that fraction, I'm going to flip it. Both the numerator and the denominator need to flip because it's going to be distributed. 4 goes into the denominator, 5 goes into the numerator, and that exponent becomes positive. Let's take these rules and put them together now. We're going to simplify this expression. It is big, it is gross, it is ugly. There are multiple different ways that you can choose to use the exponent rules to simplify this. Doesn't actually matter which order you use those rules in. You see one way to do it, I might see a different way, somebody else might see it a completely different way. That's okay. So long as you are following the rules correctly. The order that you follow them in is completely your choice. So when I looked at this, the first thing I said is that I wanted to take those numerator and figure out what was the same base so I can add those exponents together. I've got 2 x's and I've got 2 y's that show up. So I'm going to say x to the 5 plus 4 times y to the negative 2 plus negative 3. And that's what I did. And you would think that the next logical step would be to actually combine those together. I did not. Don't ask me why. I'm honestly not sure, but I did not. I moved down to my denominator and I took that 4 exponent and I distributed it to everything. Now, when we do this, it's super important to realize that 3 and x are 2 separate bases. 3 has an exponent of 1. We never actually write when it has an exponent of 1 because we just don't, but it's always secretly and visibly there, just like when we're multiplying by 1. So this 4 needs to be distributed to that 1 for the 3, which gives me 3 to the 4th. This 4 needs to be distributed to the 2, so we have x to the 8th. This 4 needs to be distributed to the 5, so we get y to the 20th. Remember, we're multiplying all of these. And then 4 needs to be distributed to negative 2. And 4 times negative 2 is negative 8. So that was what I did next. Then I went back and actually added those exponents up top. So x to the 5 plus 4, y to the negative 2 plus negative 3. I actually combined those. 5 plus 4 gives me 9. Negative 2 plus negative 3 gives me negative 5. So I got that. Then I was like, we got to get rid of these negative exponents. They can't be here. We've got to move them. We need to flip them over the fraction bar and make those exponents positive. So that is exactly what I did. Then I noticed that I have 2 sets of z's up top and 2 sets of y's on the bottom. So I'm going to go back to that power rule and I'm going to combine those. I'm going to add those exponents. And this time I actually did. So 6 plus 8 is 14, 20 plus 5 is 25. So I added those exponents together. Now I'm going to look at using that quotient rule, right? Same base being divided, I'm going to subtract my exponents. Now when I do this, I realize that 3 to the 1st and 3 to the 4th, I realize that there are more 3's in my denominator than there are in the numerator. So when I subtract, I'm still going to do 4 minus 3 and get 3. But my answer is going to stay in the denominator because that's where more of the answer was. X to the 9 over x to the 8, 9 minus 8 is 1. There are more x's in the numerator than there were in the denominator. So my final portion of that answer is going to stay in the numerator. So now I'm going to look at the problem that I have left and see, Is there any other 3's that I need to take care of? Is there any other base of x that I need to take care of? How many times does y show up? Where are all of the z's at? And once I realize that all of my bases only show up one time, my problem is finished. So let's recap what we've learned. We can now define all 7 of our exponent rules, and we can use those rules to simplify expressions with exponents. Definitely a lot. But until next time, I will see you later. Love you, bye.